So this is the last lecture of this sequence of 4 lectures we did on CAT. And what I want to do today, I want to basically show you netcat. And really, I'm not going to be able to show you all the details, but I want to give you a glimpse of what you can do with this language. And then I'm going to add some references if you're interested in learning more. There's a bunch of references I'm going to add. In fact, one reference I forgot to add. Sorry, I'm looking at the scribes who helped me with this. There's an upcoming PLDI paper that I will mention. And if I forget to give you the link, please remind me. OK, so what is netcat? We started yesterday. Netcat is a cat language that has interpreted actions and tests. And the way to think about netcat, and I will show you the semantics in a moment, is that these tests and actions operate over a packet. And for the purpose of the semantics, we assume there is one packet. Okay? And you can then generalize this to multiple packets, but to write down the semantics is easier to just assume there is one packet. And so given a packet in the beginning, you write down a regular expression where you use as actions and tests f equals n or f gets n for different f's and different n's. And in the end, you get out the state of your packet as a set of packets. And I'll show this in a second. Okay? Now, in the original netcat paper, and if you look at it, you will see this, there was also another special action called dupe, which back before the paper was published was called OBS, for observation. And the idea behind this special action, somehow OBS is a better name, but we ended up going with dupe. The idea behind this special action is that when you have a network, and I'm going to just sort of write something here that is very simple, but if you have something like this with 4 nodes, and you have your little packet coming in, maybe this little packet gets multicasted, and a copy of it ends up going here, and the copy of it ends up going here. And eventually, both these copies make it here in some order that you might not know anymore where the packets came from. So as a packet goes through the network, you might, for very specific reasons, want to remember that the packet visited a node. And so this action dupe, or OBS, when placed in your program, takes a snapshot of what the packet looked like at that moment. So if I write something like f becomes, let's use some more meaningful f. If I write switch becomes 2, dupe switch becomes 5, which is a really silly program, but doesn't matter. What this says is I have a packet, I don't know even from where, but somehow I'm going to send it to switch 2. And I'm going to remember every single packet that came in switch 2. And then I'm going to send it out to switch 5. So this dupe here in the middle just sort of remembers the state. And what I'm going to do today, I'm going to sort of forget about dupe for the semantics, just to sort of show you a simpler semantics. But if I have dupe, instead of using just packets in my semantics, I need to use sequences of packets, which we call histories, that basically keep track of the changes that the packet suffers through the network. And for some network properties, you really need dupe, because you really need to know. So if you want to say something like, an SSH packet has never visited switch 3, then you need to somehow, you can do that in 2 ways. You can either put a little monitor, say if this is switch 3, you can put a little monitor there that just keeps track that no SSH packet comes in. Or you sort of memorize everything that goes through switch 3, and then at the end, when you have all the traces, check that no SSH packet went through. So dupe gives you a little more flexibility about how fine you want your behavior to be. If I don't have dupe, then then my semantics is going to be a function from packets to packets, from packets to sets of packets. Because the only thing I can say is, my netcat program is an expression that takes a packet in. Let's use pi for packet. And based on what pi does and what e does, at the end, I'm going to get a set of packets. So for instance, if my netcat program is just f becomes n, then what I'm doing to my packet, I'm just basically saying that my packet is such that f gets rewritten, whatever value f had gets overwritten with n. If I have f is n, then either the packet does not have n in f, at which point the semantics is empty, or the packet has n in f, and that I will keep it. So this is a test, right? So for tests, you either keep things or you throw them away. That's how we think of it. And then things like plus. So plus in netcat, the semantics is union. But the way we think about it operationally, from a network point of view, is multicast. So you can think of the plus as giving you the option to do multicast. Okay? And sequential composition. Oh, let's not use F. E prime. Sequential composition is what you might expect, which is the union of all E prime pi prime for all the pi prime, all pi prime that are in E of pi. Because E of pi can produce multiple packets, so I need to sort of send them on to E prime and then take the union of all those sets, and the board is scored. Okay. So this is the sort of operational semantics of netcat. You can instantiate the guarded string semantics I gave you for cat to netcat as well. And you get then a much more sort of declarative semantics of traces, where now the tests, right? So you have your, you get these strings alpha 0, and now the actions. So for netcat, the actions here are going to be what we call complete assignments. And this thing here is a complete test. So what do they look like? So remember that I have a finite list of fields like F0, F1, Fk. And now an alpha, so before my variables were Boolean. So the only thing I needed was to see if, if it's true or false. But now my variables can take values out of a finite set of values. So what I have here for complete tests, for every field, I need to tell you the value n, which is true at that moment. Pretty much I need to tell you, if you run a test on F, which one is going to give me true. Okay? And for pi, it's the same thing. So in fact, it just looks like that. It tells you for every field, what would you assign to at that moment. So in the case of netcat, atoms are isomorphic to actions. So the set of atoms is actually isomorphic to the set of packets. Why? If I tell you for every field what I'm going to write in it, that's in one-to-one correspondence to telling you for every field what can you test through in it. It's just a change in perspective. So it's an, it's an isomorphism. And so in the netcat papers, we sometimes switch between the two without justifying it, but we try to be consistent so that you know if we're assigning or testing. But it's isomorphic. So from a semantic point of view, I could throw away actions and just keep the atoms. It doesn't really matter. But to be a little more careful, the semantics, the declarative semantics are strings like before, where the atoms are these generalized things and the actions are these complete assignments. Okay? Okay. Let me now tell you the full definition of a netcat, because we're still missing something. So a netcat is a cat that has these special actions and tests. And then a netcat satisfies all the axioms of cat plus what we call packet axioms. Okay? And the packet axioms look as follows. There's 8 of them. Let me see if I don't forget any. Let me remind myself. I showed you some yesterday. Okay, so there's 8 of them. So first one is the one I showed you yesterday. Let's use F. F becomes N, F becomes M is the same as F becomes M. Because every cell in my packet can only hold one value. So if I write one value followed by another value for the same F, that's it. I mean, I can only keep the last value. If I write values to different fields, on the other hand, then this actually has the property that I can turn them around. Because I'm sort of accessing different parts of the packet. So it's a little bit like when you're writing, these axioms are the same axioms that you will see for global variables in certain calculi. Because you're just saying, I have 2 variables, I'm writing values to them. They are in different parts of the memory. They shouldn't interfere with each other. Okay? If I have just written N to F, and then I test that F has N, because this is a language with no effects, this is the same as F has been assigned N. Okay? If I have tested that F has N, and then I write N to it, then that assignment is useless. Okay. 1, 2, 3, 4. If I test all the values in a field, if I test for everything I have in my value set, and this is where the finiteness of N of val is important, because I want to be able to test all of them. This has to be true. This just says every field has at least one value in it. So it's never undefined. But it cannot have 2 values. And when I write N and M, I'm implicitly assuming N is different from M. Otherwise, same thing here, right? I mean, okay, I'm still missing, how many am I missing? 2. What am I missing? Oh, I'm missing the dupe axiom, which I can tell you about. Somehow I cannot see which ones I'm missing. I'm becoming.
Are you missing the one where you assign and then you test for a different value?
Yes. Which one is that one? Sorry. Oh. So let me see. I'm going to write the one for dupe, just for. So if a field is n, and I dupe, so I remember that that field is n, then this should be the same as I first remembered what was in there, and then I test, and it's still n. This just says remembering the state does not change it. Okay, whatever test was valid before I remembered has to be valid after I remember. Okay, now I have 7, so I'm just missing 1. It's getting better. X becomes n after y becomes m. I have that one there. X becomes. No, do I have that? Yes, no, I don't need that one. That one I can derive. I'm completely blind. Oh no, I know. Sorry. I have an analog to this one with a test. If I have f becomes n, and now I test some other value for g. This is the same thing as testing for g, and then assigning f to n. It's again a non-interference. These are non-interference properties. Okay? Okay, and so then the result is that if I take cat plus these 8 axioms, I can prove that if two net cat expressions have the same semantics, if and only if they are provably equivalent with the axioms. Okay? And these semantics here, the double bracket, can be this one I wrote here, which is sort of an explicit packet filtering semantics, or can be this one that you derive from cat. This, in fact, in the paper, we show they are equivalent. Okay? Now, as always, these axioms are nice and algebraically super interesting, and that's why we love them. But when you want to use this in practice, you want to do a more efficient checking of equivalence. And so in the second paper we have on this, we showed that netcat has a automaton model and this automaton model gives you a decision procedure for equivalence that is quite efficient. And the key of our first decision procedure were matrices, maybe unsurprisingly. This automaton model also was used then to develop a compiler that compiles netcat expressions to a language called OpenFlow, which is a sort of, think of it as sort of an assembly-like language for software-defined networks. These days, the rage in that area is another language called P4. P4, if you've seen P4, looks almost exactly like netcat. It's kind of a fun, so it's a packet processing language. And it allows you to do things like assign headers, take pieces of the header. I mean, it has much more on top of netcat, but it has all the basic things like assign headers, test headers, and whatnot. Okay, and this compiler was based on the automaton model, But instead of using matrices, it used BDDs. Or as Stefan called it, FTDs, because they were a little more expressive than BDDs. And just in a couple of weeks at PLDI, there is a fresh, out-of-the-press new decision procedure where this automaton model has now been implemented on a BDD on steroids data structure. And the reason why it's sort of a BDD on steroids is because it allows, so in BDDs, what is a BDD? A BDD is a very efficient way to represent a function into the Booleans. Okay, so it's a function that goes from a set into another set into the Booleans. Okay? But in netcat or in cat, as you've seen, we have these values around. And especially in netcat, where we suddenly have all these, maybe fraction of natural numbers that we're assigning to fields, a BDD is definitely not enough. And so when Stefan Smolka did the compiler back in 2016, he came up with a slight variation of BDDs called forwarded decision diagrams, where the output didn't have to be binary, but could be a value. What we did in this recent work was to actually embrace the fact that in netcat, there's this alternation between atoms and assignments. And atoms are actual BDDs, because they are, you can write them as a BDD pretty much. But assignments have a very different nature, because they are changing what the packet does. And so we basically came up with this structure that is what I like to call a two-sorted BDD, which basically has two types of nodes. So it's like a two-layered BDD, where the round nodes are tests and sort of are organized in the same way as a BDD. But then there's a diamond node that actually changes the value of the packet. And that diamond node has things like default values like BDDs. So they also have a BDD-like structure. And if you look at the paper, the idea is very simple. And it doesn't seem very promising when you look at it, in the sense that why should this be more efficient than matrices or FTDs? But as it turned out, from the nature of how netcat works, this is very, very efficient. And more interestingly, at least for us, this structure actually enables us to extend netcat with things like intersection and complement and all kinds of operators that we didn't have before. And in fact, operators that are very hard to implement in the matrix world. So this kind of turned out to be a much more flexible structure, and it sped up the decision procedure like in the hundreds of times, depending on the topology. Okay, so this is sort of an overview of, if you like this stuff, an overview of papers you might want to take a peek at. But what I'm going to do for the rest of the lecture is to actually show you how you use netcat sort of to model a network, and how this works in practice to check properties with netcat. So the view I'm going to take of a network is going to be super simplistic. I'm going to assume that there are these boxes. And these boxes can do what? They have ports coming in and out. And inside each of these boxes is what is called a match action table. And then you can think of a match action table as a big if-then else. You sort of you have a table, and the table tells you things like, oh, if the type of the packet, so it gives you tests on the packet. Things like if the type is SSH, drop. If the destination is 3, then make sure that the port is 5, and so on. Okay, so in essence, each of these ports or when packets come in, packets based on this match action table, packets will go out through some port. They might even be multicasted through multiple ports. Maybe here I write multicast on port 3 and 5. Or maybe a certain packet just gets dropped. Okay. So this is what these boxes do. They are very simple. There's nothing really very complex going on in these boxes. And so for every table like this, I can basically write down a netcat expression by basically taking the test followed by the action plus the second test followed by the action plus the next test followed by the action. It's just a big sum of tests followed by actions.
Can you test that check multiple things instead of just one?
The question was, can I write tests that check multiple things? Yes. I don't have space there, so I'll write here. You can test things like this packet came in on port 3, and its destination is 5, and its type is not SSH. Yeah. Okay, so given each of these boxes, let's say that this box is switch K, the netcat expression corresponding to its behavior is of the shape I am in switch K, okay, and I'm going to take a big sum for every line of this match action table. Let's call it for every L, for every line there. I'm going to look at the test in that line, and I'm going to sequentially compose it with the action on that line. And that's it. So that's the netcat expression that captures the behavior of switch K. Okay? And if I now, I can do this for every switch K. But now I also want to capture the fact that I can connect these switches in different ways, right? So how am I going to capture that? Let's do it here for a second. I look at my network. Oh,
yeah,
sorry.
about the last part about the sum. Does this mean that every test has to be paired with at least one action, or can one or the other be empty?
So in this setting where we have the table, the only thing you have is sometimes at the end you might have a default case that says, for anything else, drop, for instance. I don't know, something like that. And so one of them can be empty or can be like default. Yeah.
Is the order in the entries of the table important in the sum?
So, right. You caught me there. Thank you. Yes. You have to be a little careful in reading the order because this is really, you should be going bottom up. So this sum is a little bit oversimplification of what I wrote there. But you can do that by basically taking this test here as the first test. When you get to the second test, you take the conjunction with the negation of the previous one, and so on. So you can still write it as a sum like this. It's just that for every Ln plus 1, you need to sort of remember that it didn't pass any of the previous tests. Okay? So I wrote it like this because the expression looks a bit nicer. But yes, you are right. Always. Yep.
In the second entry where you have port assigned to 5 plus port assigned to 3, is that like a non-deterministic behavior? Or?
So the question is, in the second line here, I have the action says port assigned to 5 plus port assigned to 3. In operational terms, this is a multicast. I copy the packet, and I send it both on port 3 and 5. So I like to say that netcat is actually deterministic, even though it looks non-deterministic, because in essence, you're like copying the packet, and the moment you copy it, they become different packets. I mean, because then they go through different lives. Okay. Right, so now on to the, so we know how to encode the boxes. And now these boxes are connected by some wires, some topology. And so let's imagine that this is box K, and this is box J. And they are connected on port 1 and port 2. Okay? So I want to represent the effect that if a packet is here on port 1, then magically it gets transported to port 2 because there's a physical link that allows me to go. I'm assuming these links are perfect, nothing goes wrong, which is, you know, it's a big if. But for now, we assume an idealized world in which the effect of a packet making it to the beginning of the link is that it has to move to the other side. So what does that mean? We actually saw the first netcat program I showed you yesterday is actually pretty much what you need for this. It says if I'm at switch K and at port 1, then I immediately want to make sure that I move to switch J and to port 2. Okay? So this is basically telling me my packet got transported from this point into this point. Okay? So this is a link between K and J. And there can be many links between different switches at different ports, between the same switches at different ports. But let's simplify and imagine there's just one between K and J. Then the topology of my network is again a sum for all the links of LKJ. I have this set of links, and I just take the sum. So this is kind of what is cool about languages like netcat and others that are based on Kleene Algebra, is that you can build, like the way to build larger and larger programs is to just use the operators like sum and sequential composition. And that gives you also the power to reason about programs like topology or the switch policy. So the switch policy, the whole thing, is going to be the sum for all switches of, what are we going to call this, SK, of all the SKs. Okay? So now I have an expression that captures the topology and an expression that captures the switch. And now how do I capture my whole network? Okay? So my whole network, what does it do at any moment? Let's imagine with this, we have a discrete breakdown of network taking steps. Okay? At every moment, I have packets somewhere, and I make a move by sending all the packets that have made it to a port. I flush them into their next destination. And after I flush them into their next destination, they get there, and they have to be treated by this match action table. Okay? So one step of the network is just this. And again, we're building this sort of compositionally. Okay, so I have the topology that tells me how the packets, if the packets are already ready to go, where do they go? Once they get to their destination, they get processed by whatever switch they are at. And this is all ensured by these tests, right? So here I have lots of switches, but every packet that gets through this sequential composition only gets processed by the switch in which this test passes, which is where it is at that moment. Okay? And now, I can just put a star around this. And if I put a star around this, I now have the multi-step behavior of my network. Okay? And you can, I mean, this direction, like which sequence I do top and switch, doesn't matter. It's just a matter of what do you do first. Do you process the packets or do you flush them to their next destination? And you see that if I enroll this network, it really won't matter because I'm doing the multiple steps. Okay? This is it. This is my network expression in netcat. Okay, so let's write down now what can you do with this. So you've now spent a lot of hours encoding some very complex network as a regular expression. And what do you do now? Of course, I mean, I guess this is clear. This process can be made automatic because the translation from a match action table to an expression is all very like, there's nothing to be thought. Like you just go from this to a big if then else and write it in netcat. Okay, and the same thing with the topology. Once you know the links between the switches, you can write a little program that translates from whatever language you have this written in to netcat. So it's not like you need to spend many hours writing this by hand. Okay, so what can I do now? I have this expression, and what can I do? I can do a few things with the vanilla netcat. I can do one very big thing, is reachability. And before I started working with reachability, before I started working with Nate on this stuff, I didn't know, but apparently, if you're a network operator, a lot of your time you're doing reachability queries. You're just checking if nodes are connected to other nodes. And so it's very important to have efficient ways of talking about reachability. Okay, so what does reachability look like in netcat as a netcat property? So let's talk about point-to-point reachability. So I have some switch A and some switch B. And I want to ask the question, I can get from switch A to switch B somehow. So if there is a packet that will transport me from A to B. So what can I do? Well, I have my network expression that tells me how I get from A to B. So what I can do, I can say, well, either A and B are directly connected by the topology, and therefore I know that there's a link between A and B. Or if they are not connected by the topology, then I have to be able, what did I call that? Switch. I have to be able to somehow take several steps and make it there. And so here now I've sort of unrolled that expression a little bit, just to say that the quickest way to get from A to B is if I can just take a direct link. But if I cannot take a direct link, then maybe I need to move my packets through the switch policy to move somewhere else that then allows me to get a direct link to B, right? So how is A connected to B? Either I have that, or I go through some C, potentially in many steps, not necessarily in one step, and that C allows me to go to B. In fact, the simplest way is that C is connected to B. Okay, but I need to take multiple steps to get to C. Okay, so this is what this says. So this says I start in A, and I try to make a hop. If that hop doesn't bring me to B. It will bring me to some place, which then, in multiple steps, allows me to get to B. Now, this is a netcat expression that talks about A going to B. And if I now can test that this expression is false, I know that A is not connected to B. Okay, let's go through this again. The expression here on the top tells me all possible ways that A would be connected to B. If those all possible ways are equivalent to the empty set, it tells me that there is no way. So reachability is, I do this equivalence query in netcat, and if it returns true, then I'm doomed because there is no way. And if it returns false, I know there is a way. I don't know what way, but I don't care. There is a way. And as it turns out, this test as an automata query is extremely efficient. This is called an emptiness test. An emptiness test. And this can be done extremely efficiently. So when we originally implemented this test for netcat using matrices, there was another tool at that time called header space. And the netcat test was about 100 times faster, even though header space had been designed specially to check for reachability. So it's kind of cool that a non-tailored technique, because this was non-tailored in some sense, it's just an algebraic view on the problem, and we use automata. It's kind of cool that somehow, as a side effect, you got a very, very efficient way of checking a property that is very important. You can go from here and check things like all pairs reachability, which is another property that people care about. So you can like make A and B a variable and take a big sum. So if I look at the big sum of like A and B being arbitrary switches, then this gives you all pairs reachability. And again, I just check if it's 0. If it's 0, it tells me that there is a pair for which this fails. Okay. What else can we check? Let me see. Yeah, forwarding loops. This is another property that sometimes you might want to check for networks. So what is a forwarding loop? A forwarding loop is when a packet keeps going through the same sort of state again and again. And, like in practice, the way this is sort of broken, like this, the way you stop a loop is basically by having a time to leave field that keeps getting decreased. And when it reaches 0, the packet disappears from the world. Okay, so if it's going in a loop, at some point it will get dropped. But you might want to check if your topology or your switch policies is inducing such forwarding loop. You might just want to syntactically make sure that this is not there, that by mistake you didn't introduce a forwarding loop. And the reason why forwarding loops are important is that they have been the reason of major outages. And there's, I think, a recent one, I forgot when, a few months ago, that was basically just caused by a misconfiguration that caused a forwarding loop. So how would we check this in netcat? So you basically take an alpha, so one of these states, and you check that this alpha, so let me write this in 2 stages. The first thing you check is whether, for some alpha, and I will tell you which alpha, when you run your network, you basically, let me just use Oh, the same notation I used over there. When I run my network, when I'm running my network, I do not want to be visiting the same state over and over again. Okay, so this is the same state. Remember that this describes all the fields in a packet, including its position. Okay, and I don't want to be visiting the same thing over and over again. But for which alphas do I need to check this? If I need to check them for all of them, is a bit much. So I only want to check them for the ones in which I look at the ingress predicate. This is just the points in the network where packets can come in. So it's just a sum of ports and switches. So the packets come in here, and then I have my network. And basically, I look at all the alphas that can be generated from going through my network, and they don't vanish, meaning they are still there after I went multiple steps. And this sort of generates a number of alphas that hopefully, in many cases, is relatively small. And then for all those alphas, I do this check. And this check is, again, quite efficient to check that this expression is not equivalent to 0. Okay? So the forwarding loop case is a little more involved because you first need to compute which packets you need to then run this check for. Okay? And again, just to be clear, the check you're going to do is that this is equal to 0. Okay. I think I have time to show you one last example that's a bit more involved. Yeah, let's do the following. Are there questions? Yes, Thibault.
Just about the remark that you made before, you said if we want to check for all pairs, then we do the sum and we check whether it's 0. I don't think I understand why.
Did I?
If it's 0, I have the impression that it would tell you that there are no pairs, that all the pairs.
Right. Sorry, sorry, you're right. Yes, good point. If you do the sum, you get that all pairs. You get that no pair is connected to no pair. If you want to do all pairs, you need to look at every summand individually and check that every summand is non-equivalent to 0. Yes, good point. Sorry, I shouldn't have written the sum. Yes.
I didn't catch something you said around the same time. Did you say that the old process used matrices to calculate that, and NetCat doesn't deviate from that?
No. So the original decision procedure used matrices and was already much faster than state of the art. But now we have a few new implementations. One of which, the most recent one, is coming out in 2 weeks at PLDI.
So what NetCat originally was doing was a bunch of sequential matrix multiplication.
It was more smart than that, in the sense that we use these things. So the matrices are quite sparse. So when you write the matrix for a NetCat expression, it's a quite sparse matrix. So we used something we called spines, which was basically just looking at the columns where there were values. And we used those columns to do equivalence. And then at the end, we rebuilt the semantics. So it was a little more complex than just using the matrix. But it was basically exploiting the sparsity of the matrix. This is a hard word. Okay, let's see. There, and then there. Okay.
So the forwarding loops you mentioned, you can filter your alpha to only the reachable states.
To the states that don't vanish, we call them. So these are states that your network does not, eliminate.
So how do you do that filtering to write your query?
How do we get the alphas? You do a sort of backward reasoning on the expression. And this is, again, appears in the PLDI paper, actually, a way you can do this. You basically look at all alphas, but symbolically. And then you sort of feed them back through your expression to see if there was a way they could have been inputted in. So it's kind of a bottom-up approach. Yeah. So in our PLDI paper, we explained this a little bit about symbolic manipulation of packets traveling through a network and how you can sort of go forward and backwards and mixing even both to check which packets you have at any moment. Yeah. There.
So ideally, if you fail a check, you also want to know why. So something analogous to like an unsack or a resolve.
Very good. The question is, when you get a fail, you also want to know why. In this algebraic view of the world, you wouldn't know why necessarily. But as I said, the engine that we implemented uses automata. Therefore, whenever I see that it failed, I can backtrack why it failed. And going back to what I mentioned, in the PLDI paper, we actually show how to compute all ways of failing, like all possible ways that it would land in that failure state. And you get a symbolic representation of the packets. So yes, so in practice, you do want to know why you fail. And not only you want to know why you fail, you want to display while you fail in a symbolic way that, say, a network operator could understand. Yeah. I had one here, and then I'll go back.
Okay. So I think the netcat can be viewed as a kind of network protocol verification, right? So previously, when people are doing that, they may use model checking or logic-based algorithms. So what's the advantage of the cat upon the logic-based or model checking algorithms?
Okay, so the question is, what is the advantage of cat compared to things like model checking? Okay. There's not a real like black and white answer. So I'll tell you several things that I think are nice, and then I'll also mention in reply, someone mentioned Ansat cores. I want to say something about that as well in a second. So from a sort of declarative point of view, the way Netcat was designed and the reason why we believe it's a really nice language is that there is this sort of, at the same time, it's a programming language. You can translate it into P4, OpenFlow, but it's also a programming logic. So the properties, this is a language in which you write your programs and your properties in the same language. Therefore, checking properties go immediately hand in hand with your semantics. So you don't need to be going back and forth between a different logic and the language. Okay, so that's one advantage. The other advantage is if you do model checking, you need a model, a Kripke model, or some form of finite state model. And that is not necessarily compositional. So if I give you a program, some network program, and then I tell you, oh yeah, I added 3 more switches to it, then you need to rebuild your model. In Netcat, one of the major advantages, and what we exploit a lot in the verification tool, is this compositionality. You can break things down with the operators, and sort of like everything is very seamless. And in the PLDI paper, we now have other operators that allow us to even more expressively breaking it down. We have intersection, we have complement. So that is sort of a nice thing. Now, having said all of this, right, we're building a tailored tool. Is that smart? When model checking has been there for 30, 40 years and has all kinds of really well-studied tools, it's research. It's like I have fun, Nate has fun, our students have fun. I should probably be saying this on camera, but sometimes you do things for fun, and they turned out to work like beautifully, and you're like, whoa, this actually can be used, and it's great. And Nate and I the other day were laughing about this. The original paper for Netcat appeared in 2015. And we really thought, and our decision procedure was 2016, and we really thought there was nothing else to be said about that. We thought, yeah, it's sort of done and dusted and implemented and beautiful. And then 2024, right? Here we are with a new data structure. Why? We got to talk with some people at Galois who were really interested in making this more in production, like really making a tool that can be used at scale. And yeah, in these chats, we ended up coming up with this new data structure, which is, in my case, is a really beautiful, actually, insight on the structure of Netcat. And we have a tool that is freaking fast. It's kind of, kind of fun. And like, did we have to do this, or like, does this bring anything else to Netcat other than practical application? Probably not. In terms of the theory, we still think our 2015, 2016 paper are pretty extensive in what we presented on Netcat. But from a practical point of view, there's much to be done, and people are interested in it. So I think, there's that. Now to make a comment, like in some of the things we looked at, we did think about using SAT solvers and how to use the NSAT course to sort of give us more insight on the counterexamples. Of course, again, maybe not super well justified, but our bisimulation-based tool just offered a much more direct way of computing the counterexample that then looked like a packet trace, which is much easier to share than with the people who actually operate on this, on the program. So yes, you could use a SAT solver, but then you would have to have an interpreter for your traces that actually goes back from what the SAT solver gives you as an NSAT core to what the counterexample looks like. And maybe that's easy. I don't know. I haven't tried it, so I don't know the answer to that, but it's still a step. Yes. Hey. So we, meaning Nate and I and our students can't, but there's a group at Princeton that has something called the temporal netcat, and so they can do temporal properties. Yeah, sure. Yeah.
Other problems are would it be like worth to look into applying the SPPs to other decision problems, or is this netcat specific?
That's a very good question. I haven't thought about it, so I don't want to say yes or no. Maybe. I will say one thing. Netcat has this, and CAT in general, has this thing, as I said yesterday, we kind of ignore the infinite traces. Our semantics only looks at terminating programs and programs that give me finite traces. And everything that is non-terminating, we say they are all the same, and by the way, they are equivalent to a board, which, again, I said this yesterday, this is debatable. So as the semantics stand, there's no like Buchy-like construction happening, which simplifies life quite a lot. So I don't know if what we have and our data structures can easily be extended to take into account things like I visit this state infinitely often, or I do fairness conditions or something like that. I just don't know. Yeah. Yes.
Very minor question. I think I missed it. What is in?
Okay. The question is, what is in this expression? In is just a predicate that tells me what ports and switches I can come in, packets can come in. So typically in a network like this, you might want to isolate part of it and say that only A is accessible from the outside, from the world. And so in might be just these 2 ports on switch A, and then all the rest happens in the network, but no entity from the outside can send packets into B, for instance. So in is just telling me, how can I get into this network? So it's just a big sum of ports and switches.
And with the equals 0, so is you have a forwarding loop at 0, or you don't have a forwarding loop at 0?
So here, if this is 0, then you do not have a forwarding loop. Yeah. Yes.
I wonder if you can track properties like shortest distance between
Ah.
some distance to find all that.
That would be nice, wouldn't it? Yes. So yes and no. Yes, there is an interpretation of these things in which you attach a weight to every action. Now, what is tricky here is that you actually don't want to attach the weight to an action. You want to attach the weight to the link. And that's a little more difficult, because it would mean I would have to make links first-class actions. And that doesn't sort of like mash very well together. But in CAT, in general, you can talk about shortest paths. by giving the actions a weight. Yeah.
Are you able to encapsulate multiple switches in a network so that like inter-network communication can just be captured by one relation, like encapsulate all the switches with as if they are just one switch?
Yes. In the original paper, there's something we call the big switch, which is basically doing that. Yeah. And this is where oh, sorry. Thank you. The question was, can we encapsulate all switches so that it looks like one thing? And the answer is yes. So you can talk about like a big switch in which inside the switch there's a little network. And this is this is sort of the beauty of this compositional reasoning, is that I can just like talk about what the switch does and then name the external ports of that big switch and just expose those to the user. And all the rest is sort of a sub-expression that I don't show. Okay, more questions. Yes, Anna.
So about expert networks, so I'm just trying to guess, what is the concurrency element of this?
Very good question. What is the concurrency element here? Here, none. So I assume this perfect world in which I have one packet. So no concurrency, no global state that can communicate. Once you add concurrency or any other effect, then life becomes harder. But for reachability, again, for these properties that are interesting, you don't need to talk about concurrency. And therefore, the way we think about netcat, and in the slides I have this nice example. I have a picture with cats that sort of illustrates this. I don't know if you guys ever saw, there's a book called The Stack of Cats. And there's like, I cannot draw cats, but there's little cats stacked on top of each other. Imagine these are cats. Anyway, this is how we think of this work that we've done along the years. It's like as a big stack of cats. And so we have KA, and we have cat, and we have netcat, and we have prob netcat, which is a probabilistic version of netcat. And then we wanted to have concurrent prob netcat. That was the dream. Except the cat fell down, and it turned out that this is not possible as a stack. And when I write the stack, what I really mean is that if you go up the stack, the semantics and the algorithms sort of extend conservatively. So if I restrict my netcat to talk just about uninterpreted actions, it's just a cat. And if I restrict cat to have no tests, then it's just a KA. That's what I mean, right? You can go up and down seamlessly. When you add concurrency to it, it turns out that KA is not quite the right core. You need a slight modification, actually more at the cat level. You need a slight modification of cat to talk about concurrent cat. And that throws the T away. So the T is a Boolean algebra. And it becomes an O, which stands for observations. Because suddenly the tests are not atomic. So you sort of like every time, this was the chicken example I gave some lectures ago. Like in the T world, in the Boolean algebra world, if the chicken looks left and the chicken looks right and there's no car, there's no car. But in the concurrent world, if the chicken looks left, there's no car. The chicken looks right, there's no car, and she gets hit by a car. Because in between, let's say by a bike, so that there's some chance of survival. Because, like if I look left, while I look left, the right thread might be now writing in the variable. And like the left variable suddenly became false. Okay? So because of that, all this stuff we know about cat suddenly becomes not very helpful. And so you need to rebuild the tower to take into account that you don't have a Boolean algebra anymore. You have something a little more complex. And that little more complex, which is not that more complex algebraically, sadly, makes the algorithms much more complex, and the semantics as well. The semantics suddenly is not a set of strings or a set of traces, but it has to have trees, and those trees have to be closed under a certain order that tells you in which order sort of the actions take place and the tests, and it just becomes extremely sort of ugly. And, you know, at some point you need to choose your battles, and so far we redid CAT, that's done. We sort of redid netcat, but we're not fully happy with it. So we're not going to go up the tower until we're happy with what's happening here. And so we're still working on that. So yeah, I forgot what the question was about concurrency. Sorry, I went on this ramble, and suddenly I didn't know what the question was. So the adding concurrency or any effect is really hard. That's sort of the message. But you can do a lot without concurrency, which is also another message that sometimes, I mean, in PL and in general, we try, when we start designing a language, we want everything in, right? You want everything because it looks cool. But sometimes there's value in just asking the question, what is the absolute minimum I need to do this important verification task, right? So this is the question that we ask to do reachability. What is the smallest language we can come up with so that we can do reachability in an efficient way? And then we went from there, and we can do things like slice isolation. You know, we can do a bunch of like really nice network properties just with vanilla netcat. No extension, no syntactic sugar, nothing. Okay, and in the PLDI paper, we showed that if you are able to have a few more operators, then you can do it in a nicer way and closer to what a real network operator might write, which is kind of nice.
It feels like this is so close to having modal properties, but like a lot of the properties right now is sort of box something.
Yeah.
But it feels like a lot. Network operators often have to make a lot of diamond queries as well in terms of the topology of things. So I was wondering what would need to be added to get that.
So at the moment we don't have. So sorry. The question is. I did it before you told me off. The question is, this seems very close to have modal operators, and that seems like it would be useful because people do a lot of diamond questions, so for those who are not familiar with that, it means things like eventually something good or bad will happen. You can do that in netcat. You just have to sort of encode it outside. Sort of you can look at everything that happens. Therefore, once I give you the semantics, you can run modal queries on it. And in the first tool we implemented on this, there was some capability to sort of run modal operations. In the PLDI paper, we do not have it as a sort of external thing because the queries we were interested in didn't need it. I think it would be an interesting thing to investigate is whether you can add it on top of it as a language sort of feature that then compiles down to a bunch of queries here. So the things we have in the PLDI paper sort of work a bit like that. You have a sort of expressive query, but then under the hood, it gets compiled to a bunch of netcat queries that then reduce to equivalence. Yeah, it's a good point. Okay. This is a great audience. Oh, one more question. Yeah. Okay, so the question is, can we do anything about dynamic properties? Like if a switch is down, then reachability still holds. That is extremely important. A lot of, say telecom companies or they want to give you that assurance, like K node failure is a property. So that means that if K nodes fail, my network is still running, right? And this is the motivation behind prob netcat, where we attach to every link a probability of failing. And then there, you can reason about things like that. You can say, if these n links are down, then there's this probability that the packet gets lost. things like that. So that was exactly the motivation for extending netcat with quantities. Okay, back here.
Do you guys plan to like add like protocol primitives and stuff like TCP or maybe like distributed protocols like RAP? Because what I think is interesting, there's a lot of like formal models for RAP and for all these distributed protocols, but there's nothing like very close to the network that's still a formal model like this.
So the question is, do we plan to add protocols like TCP to this work? I think the current answer is no, in the sense that we have finite capacity about what we can do, and we have a lot of things we still want to do in this cat stack that we find interesting from an algebraic point of view. For instance, one thing we're currently looking at is adding state like a stack. We call it stack netcat. We find that really important because you want to have the ability to like be able to read, to be able to use part of your packets as a sort of data structure to memorize certain values that then you like send around the network. So that's one step closer to having a real state. The other thing we're really interested in is typed netcat. So at the moment, my values are untyped, but really, in a real packet, you have constraints. You say, I can only write a 32-bit integer here, or things like that. So we would like to basically extend this with types. So those are kind of the things immediate. And then the other thing I'm really interested in, which has nothing to do with this, but I find very cool, is to reverse engineer what a network is doing. A lot of the networks are black box. You don't have access to them. So one thing I'm doing with a student right now is you inject packets through your network, and you just observe what happens to those packets. And can you write down a netcat program that tells me what the network is doing? So I'm really, really, really into that. And I've done this exact thing for TCP, and it's a pain. So I'm happy to stick to a more algebraic world. So right now, I don't think I have these plans. I don't think Nate and his students have these plans, but could be an interesting extension. With the caveat that once you have distributed protocols, it's going to be really hard. Yeah. Yes?
Can you use netcat to answer questions about, or figure out, reducing the amount of links that you need to reach one node to another?
That is another, so the question was, can we use netcat to minimize the number of links that still keep a certain property, say like reachability, right? That is another, optimizations is another thing we actually have on our list. And in this work we did on SPPs, and that we are continuing with this company called Galois, which is a really cool company. If you're looking for internships at some point, I very much recommend. That one of the things we have in the sort of the next steps is to look at QoS, like quality of service, and also at possibly optimizing how many resources you use and still have the same functional behavior. Again, these things get really tricky with concurrency because you might think you can remove a link, but then this was actually not fully correct. So you need to be a bit careful. Like if you remove a link, you have to just be extremely careful that the property you're trying to still remain as an invariant doesn't then affect some other property in the network that you didn't check. But yeah, optimizations are really, would be really cool. And that's something we have on the pipeline. Yes?
It's less about like netcat, but can you use something like, if you encode your programming language into something that looks like a Kleene Algebra, can you use that to do optimizations on the program that you're using?
Yes, and this is something Dexter Kozan has done with some of his students for compiler optimizations for, the question was, if I have some language and I somehow manage to translate it into a Kleene algebra-like expression, can I then use it to do optimizations for my program? And the answer is yes. but most of the time it's used to actually prove soundness of optimization. So you sort of have an optimization in mind in your language, and you're not quite sure how to prove its sound, and you sort of like use the translation to then prove soundness. And so Dexter has some examples of these in Java and in compilers and some other things. Okay. So I just saw that the time is 10:20, which means that the big example I was going to show you is not going to happen. But I will share the slides for this example because I don't think there's any sort of value in me starting the example. I'll just share the slides. It's like 5 slides, and it shows you a network for which you can analyze access control. So things like only certain packets go through. And so then I give you the netcat expression, and I show you how to prove algebraically that indeed the packets that are not supposed to go through do not go through. And then I think I also have in there the fact that you can install the policy in 2 different switches, and the property is still true, which is something that sometimes you might want to check. And with that, I will end my lectures here on time. So thank you.